This is Venus de Milo, and this is Michelangelo's David. They're beautiful sculptures. But why do we think that these artworks are beautiful? There are two ways of looking at this. One is that they are beautiful because there is the objective property of beauty in the works. The other is that this is just a piece of stone, and I have the subjective feeling of beauty when I look at it. Plato believed that beauty was an objective property of the artwork. But where on earth is the beauty? What part of the sculpture is the property of beauty? It's hard to answer a question like this. But it only gets harder. We feel beauty while listening to music. But where is the property of beauty in music? Is it in the sheet music? Or is it in the sound waves? These questions are difficult to answer. But Plato tried to give a proper answer. This is the story for today. This is Venus de Milo, and this is Michelangelo's David. This is Botticelli's The Birth of Venus, and this is Michelangelo's Creation of Adam. This is the Parthenon in Greece, and this is a woodcut by a Japanese artist Hokusai called The Great Wave of Kanagawa. They're all beautiful, and these pieces of art have one thing in common. It's that these artworks have an appropriate proportion of balance. Some people say that the proportion of these works of art is the golden ratio, the proportion which humans find most beautiful. The golden ratio is the ratio of 1 to 1.618. And the characteristic of the golden ratio is that the ratio of the rectangle after you take out a square whose side is the same as the short side is also 1 to 1.618. And then the ratio of the rectangle minus the square is 1 to 1.618. Again, the ratio of the rectangle minus the square is 1 to 1.618. This ratio, which is repeated over and over again, is called the golden ratio. People find the golden ratio harmonious. If you connect the corners of the squares, you get this spiral pattern. This spiral pattern is also found in nature. In the shell of the Nautilus, in the structure of sunflower seeds, in the shape of leaves, and also on the surface of pineapples, you can find the golden ratio. If you think about it, there seems to be a proportion that humans find beautiful, even if it's not the golden ratio. The reason why these works are beautiful is that they have a good balance and composition. Look at this composition. We get the feeling of beauty. Ancient Greek philosophers thought that the source of beauty was the sense of harmony and balance that comes from appropriate proportion. So Plato said, beauty never lacks proportion, and Aristotle said, beauty must present a certain order in the arrangement of parts. In conclusion, beauty is the beautiful proportion of objects. This is called the great theory of beauty. So that's great for paintings and sculptures. But what about music? Is there a ratio like this in music? Sound has no form, so can there be a ratio like this? But actually, that's not true. In fact, there is ratio and composition in music. Now let's see why. One day, Pythagoras was passing by a blacksmith's. He found that some sounds were pleasant to listen to, but some sounds were uncomfortable to hear. For example, he discovered that when the ratio of frequencies was 2 to 3 or 3 to 4, it produced a harmonious and pleasant sound. So Pythagoras made a scale with the harmonious sounds. Here's how he made the scale. The length of a string determines the pitch. First, say the sound from a string whose length is 1 meter is do. Then the sound made from a string half this length is also do. Because the human ear can't distinguish between a pitch and the pitch that has twice the frequency of that pitch. This is called octave equivalence. Now let's find the pitch that goes best with do. The best match for a pitch is the pitch made by a string 3/4 in length and the pitch made by a string 2/3 in length. Let's say the pitch which is made by the string 3/4 in length is fa, and the pitch which is made by the string 2/3 in length is sol. And the best match for sol is made by the length of 4/9, which is 2/3 of 2/3. But humans can't tell a certain pitch from a pitch that has twice the frequency of that pitch. So we think a pitch that's made by a string which is 4/9 in length is the same as the pitch made by a string that's 8/9 in length. So that pitch is re. 2/3 of 8/9 is 16/27. This is law. Then again, the best match for law is 2/3 of 16/27, which is 32/81. And twice that is 64/81. This is me. Then again, the best match for me is 128 to 143rds, which is 2/3 of 64/81. This is C. This is a proportion of the length of the string, and the pitch is inversely proportional to the length of the string. So if you flip the numerator and the denominator, it's this. This is the Pythagorean scale. But the numbers are a little complicated. You change me to a similar ratio of 5/4, and you change law to 5/3, and you change C to 15/8. This is called the just intonation. In this way, the major triads, do, mi, sol, si, re, and fa, la, do, all have a ratio of 4 to 5 to 6. But there is a critical problem with the just intonation, which is that the pitch changes when you change keys, because the intervals between the frequency of the notes are not constant. So this time, we're going to cut an octave into 12 equal parts. Then, do is 1, do sharp is the 12th root of 2, re is the 12th root of 2 squared, re sharp is the 12th root of 2 cubed, mi is the 12th root of 2 to the power of 4, fa is the 12th root of 2 to the power of 5, and so on. This is called the equal temperament. In the equal temperament, fa is the 12th root of 2 to the power of 5, which is close to 4/3. In the end, although there is a slight difference, the Pythagorean scale, just intonation, and equal temperament are quite similar. People can't tell these subtle differences. This is do, mi, sol in the Pythagorean scale. And this is do, mi, sol in just intonation. And this is do, mi, sol in equal temperament. So let's hear it again in a row. You can't really tell the difference. Let's briefly listen to the prelude in C major from Bach's Well-Tempered Clavier. It's very comfortable to listen to. So there are harmonious chords between the notes. We say these chords are in assonance, and there are some chords that are awkward and uncomfortable to hear. They are called dissonance. When a chord has a mathematically simple nature number ratio, it's assonance. And when a chord doesn't have a natural number ratio, it's dissonance. Just like there are beautiful proportions in visual art, there are beautiful proportions in music as well. Just like visual artworks like paintings and sculptures have a spatial structure, music has temporal structure. The pitch of a note is spread out over time, and the viewer grasps the structure by comparing the note that was previously heard with the note that is heard now. And we are constantly interpreting the structure. And as we listen to the structure of music, we feel beauty. So Plato's great theory of beauty, which says beauty is in appropriate proportions, can be applied to music. Plato's great theory of beauty was accepted without much controversy for 2,200 years, up to the 17th century. Accepting the great theory of beauty means accepting that beauty is an objective property of a work. However, several objections to the great theory of beauty were raised in the 18th century. It is that beauty is not an objective property, but a subjective feeling that the viewer has. Kant held this view. Like this, the question of whether beauty is an objective property or a subjective idea seems controversial. But putting that aside, it seems difficult to take the great theory of beauty at face value, because we find beauty in Chirico's overemphasized perspective, in the uncomfortable proportion of Magritte, and in the awkward composition in the photograph. The same is true in music. Beauty is found not only in assonance, but also in dissonance. So why do we feel beauty when we see these strange proportions and awkward compositions and listen to cacophony? We'll talk about that in the next video on aesthetics. Let's wrap up. First, Plato came up with the great theory of beauty. The great theory of beauty is that the reason we feel beauty when we see a work of art is because of the beautiful proportions it has. Because of these beautiful proportions, we feel a sense of balance and harmony when we see a work of art. Second, just as there is a beautiful proportion in visual art, such as paintings or sculptures, there are beautiful proportions in auditory art, such as music. Third, the strange thing is that we find beauty in strange proportions and in awkward composition as well.